diving deep into the world of organic chemistry for a pretty amazing molecular makeover. We're going to see how a really simple molecule can be transformed into something completely different with just a little bit of chemical encouragement.
So here's our game plan. First, we'll look at the big picture, the before and after. Then, we'll get into the why it all happens, which is super interesting. After that, we'll see the how, both on the tiny molecular level and then how it's done in the lab. And finally, we'll wrap up by seeing how chemists actually grade themselves to see how well they did.
Okay, let's get into it. To really get our heads around this, we first need to see the whole transformation laid out. What are we starting with and what are we trying to make?
So here it is, the whole shebang on one slide. On the left, our starting lineup is aniline and bromine. And our goal? To get that molecule on the right, 2,4,6, tribromoaniline. Now look closely. We're not just adding one bromine atom, we're adding 3 of them. The question that should pop into your head right away is, how? And why does it happen so easily?
To get that answer, you got to meet the real star of the show here. It's that little amino group, the NH2, that's hanging off the aniline molecule. Seriously, that small group is the secret sauce to this entire reaction.
So let's talk about what an activating group even is. Think of it like a turbocharger on an engine. It takes the benzene ring, which is already pretty stable and kind of chill, and it just revs it up, making it way more reactive and eager to connect with other molecules.
And listen, the amino group isn't just any activator. This thing is a powerhouse. It literally shoves its own electrons into the benzene ring, making the whole ring super rich with negative charge. But it's also smart. It doesn't just flood the whole thing, it's like a traffic cop, directing all that extra electron density to very specific spots, positions 2, 4, and 6, and that, right there, is the key.
And this is where it gets really cool. This shows you just how powerful that amino group is. For most reactions like this, you'd need a helper, some kind of catalyst, to get the bromine to even think about reacting. But not here. Nope. The aniline ring is so supercharged, so inviting, that the bromine just can't help itself. No catalyst needed at all. So you have to wonder, right? We've got this incredibly reactive, electron-rich ring just sitting there. What on earth happens when a bromine molecule happens to wander by? Okay, now we get to zoom all the way in and watch the action sequence. This is the mechanism. It's like the molecular dance that shows us step by step exactly how those bromine atoms find their way to their new home on the ring. It all goes down in a flash. First, as the bromine molecule gets close, that electron-rich ring pushes on it, polarizing it and making one end slightly positive. Then, bam, the attack. That positive end of the bromine slams into one of those super dense ortho or para spots. This creates a really unstable intermediate, a sigma complex. The ring hates being like this, it wants its stability back. So it immediately kicks off a proton to restore its perfect aromatic structure. And just like that, one bromine is on. And because that ring is so ridiculously activated, this happens 2 more times, almost instantly filling up all 3 spots. All right, the theory is one thing. That molecular dance is cool and all, but what does this actually look like in the real world? It's time to put on the lab coat and see how it's done. So now we're zooming out, moving from the microscopic to the macroscopic. This is the actual hands-on recipe for making our product, exactly like a chemist would do it in the lab. Okay, step 1, we get our solutions ready. One with aniline, one with bromine. Then, and this is super important, we stick the aniline flask into an ice bath. Why? Well, this reaction is what we call exothermic. It gives off a ton of heat and we've got to keep things cool and under control. Then we slowly, drop by drop, add the bromine while stirring the whole time to make sure everything mixes perfectly.
So, the reaction's done. But now our product is mixed up with a bunch of other stuff. To get it out, we dump the whole mixture into cold water. Our product hates water, so it immediately crashes out as a solid. That's called precipitation. From there, we just filter the solid out, give it a good wash to clean it up, and then, for the final step, we recrystallize it to get our beautiful, pure product.
So, we did it. We made the compound, we purified it, but we're not quite finished. Now comes the big question every chemist has to ask. How well did we actually do? Was it an efficient process?
To grade our work, we first need to know what a perfect score looks like. That's the theoretical yield. It's the absolute maximum amount of product we could possibly get if every single molecule reacted perfectly without any mistakes. It's the 100% gold star perfect worlds number.
But, of course, the real world is messy. The practical yield is the reality check. It's the actual amount of stuff you have in your flask at the end of the day, what you can actually weigh on a scale after all the filtering and drying is done.
And that brings us to our final report card, the percentage yield. You just take what you actually got, the practical yield, and divide it by what you could have gotten in that perfect world, the theoretical yield. Multiply by 100, and there's your score. It tells you exactly how efficient you were.
When you boil it all down, understanding these activating groups is like having a chemical GPS. It gives chemists incredible control, letting them tell new atoms exactly where to go on a molecule. And this idea is so much bigger than just this one reaction. It's a fundamental principle that's used to build everything from life-saving drugs to brand new materials. It's really the art of building molecules with purpose.